we're now aware of roughly how to carry out critical point analysis of a multivariable function. We're going to reapproach this problem because it is a little excessive to be doing all of the derivatives by hand. We can actually utilize technology to simplify the amount of work that we have. So in the context of reapproaching this problem, we wanted to find the critical points. So the first thing that we needed to do is to find the partial derivatives with respect to x and with respect to y. So this will be a little bit of a breather of a problem now that we can let technology help us do some of the overhead. So we still have to carry out the operations and know what it is that we're doing. But we're going to compute these two derivatives using technology. So our function is e to the negative xy. Now I'm going to go over to wolframalpha.com. So you'll type this into your browser.com at the end. And what you'll enter in here is derivatives of, and then I'll type in the function e to power, or e caret, and then in parentheses negative xy. It's critical that you have those parentheses around it because we want to make sure that negative xy appears in the exponent. We don't want e to the negative x times y down at the back at the base. So we'll press enter, and you'll get an opportunity to see how Wolfram Alpha interpreted your input. F of xy equals e to the power of negative xy. Great, looks good, that's what we wanted. And it gives us the two partial derivatives. That's what we worked so hard to find by hand. So I'm going to go ahead and take this and put it into our spreadsheet here, or our sheet. And now what we know that we need to do is we need to take these two partial derivatives, which is the same thing that we got. It just writes it as y times negative e to the negative xy. Remember, we obtained negative y e to the negative xy. And so now what we need to do, okay, so I'm just going to write those down. So we got negative y e to the negative xy and negative x e to the negative xy. That's the interpretation of our output there. And so now we need to set these equal to 0 and solve. So we need to set this equal to 0, set this equal to 0, and we need to solve this system of equations. Now this is a system of equations. It's not linear, but it's still possible to use Wolfram Alpha to help us solve it. So what I'll do now is I will take these two functions, I clear out my output here, and I remember what they are. So negative y e to the negative xy equals 0. And then I'll put a comma and a space and type in negative x e to the negative xy equal to 0. What Wolfram Alpha will interpret this to mean is solve this system of equations for me. So as we do this, you'll see that it interprets your output as the set of two equations. That's what the two brackets mean on the end there. And it shows us what the solution is. It says the solution, and it's going to give you a bunch of weird stuff which you can ignore. But then down at the bottom it gives us the solution. That's the critical point, 0, 0. So now we know that we get the critical point from this using Wolfram Alpha. We get the ordered pair xy equals 0, 0. Now the next thing we would want to do is determine whether this is a maximum or minimum, now or a saddle point. Now we already know this is a saddle point, and we can kind of see that from this direction, 0, 0 is a minimum, and we can't really see it super well, but if you take this rotation of it, we kind of see that it's a minimum in that other direction. So we kind of actually have something like this, where it's a maximum in one direction, minimum in the other direction. So here it's a little bit more evident that that's going to be, and remember that's the point 0, 0, 1 after we plug 0, 0 back into our original equation here. Okay, so now we need to conduct the d-test, so we need not only the partial derivatives, but we need the second derivatives. And I'll show you how to do that using technology as well. To do this, what we're going to enter in is the second derivative with respect to x, and that's how we type it. And now I'm not going to enter f of xy, I'm just going to type in e to the negative xy. For some reason, whenever you enter the function, it gives you a weird output. Okay, so there's the second derivative with respect to x, and there it is. Lo and behold, that's the same thing we obtained earlier y squared e to the negative xy. We could do the same thing for the derivative with respect to y. We would just change that to a y. And again, just always check the input interpretation. The second derivative with respect to y, e to the negative xy, is x squared e to the negative xy. Perfect. Okay, and now we want the mixed partial. So what we'll do is we'll change this to dx dy. And we obtain xy e to the negative xy minus e to the negative xy. Now, this is actually the same equation as we obtained. I'll write it down and I'll show you why. So here I just typed in the three second derivatives that we wrote out. Now this one that looks a little bit different than our previous answer, if you distribute e to the negative xy into the parentheses, you get xy e to the negative xy minus e to the negative xy. Now the reason Wolfram Alpha outputs the way it does is just based on the algorithm that it's using and how it computes partial derivatives. But just to see that this is the same thing we obtained in our previous video, we obtained, using the product rule, this expression here. Well, in this second term, we have negative x times negative y. These are three things being multiplied together. And when you multiply three things together, it doesn't matter what order they're multiplied in by the commutative property. Negative x times negative y is just xy. The negative 1 times negative 1 is positive 1. And then this term gives us minus e to the negative xy. And if you look at what this gave us, it's exactly the same answer. It's just in a more compact form. So now we would go about carrying out our d test, just like we did before, d of 0, 0. So we would take the second derivative with respect to x, plug in 0, 0, multiply that by f sub yy, plug in 0, 0, minus the quantity f sub xy evaluated at 0, 0 squared. And so by kind of eyeballing these, if I plug in 0 for y and 0 for x, I'm going to get 0. If I plug in 0 for x, 0 for y, I'm going to get 0. And if I plug in 0 for y and 0 for x, I will get e to the 0 is 1. 0 times 0 is 0. So we have 1 times negative 1, which is negative 1. And that's exactly the same answer we obtained previously, which gave us negative 1. And since that is less than 0, we would say that 0, 0, 1 is a saddle point. Okay, totally welcome to do it this way. Oftentimes we don't compute all of these derivatives by hand, but you can see how we still had to show some work to get to the final stage. Now here is another example, and this one we won't do by differentiating by hand, but we can see that it looks like there might be a minimum and maybe, two maxima. And this surface goes on forever, infinitely in both directions. So we'll locate all of the critical points along this entire surface. From x goes from negative infinity to infinity, and y goes from negative infinity to infinity. So the first thing we need are the partial derivatives of this, and we're going to obtain those by using Wolfram Alpha. So we need to plug this equation in. So we'll have partial derivatives of x squared plus 1 divided by y squared plus 1. And this time I decided to omit the f of xy. You don't necessarily have to have that there as long as you type in partial derivatives. And you can see that we get them to be here and here. Now, that would require a little bit of work in order to obtain those partial derivatives, but here they come pretty much free of charge. So the partial derivative with respect to x and y are here. Okay, so there we go. And now we need to set these equal to 0. And we need to solve that system. So again, we'll come back to Wolfram Alpha and we'll solve this system. So what I'm going to enter in is the first equation, 2x over x squared plus 1. I'm sorry, y squared plus 1. And I need to set that equal to 0. And then comma, second equation, negative. And we don't need the numerator in parentheses. We could just type in negative 2 times x squared plus 1 times y divided by. And now, because there's just one term there and it already has parentheses, I can just do y squared plus 1 squared. Set that equal to 0 as well. Okay, so now we just need to press enter, make sure that Wolfram Alpha interpreted what we wanted, and sometimes it will pull things out of the numerator, but this is still 2x over y squared plus 1. This is still negative 2 times x squared plus 1 times y over y squared plus 1 squared equals 0. And we obtain our critical points as being x equals 0, y equals 0. Now wait a minute, we kind of observed that these looked like they might be maxima and minima. However, what we didn't account for is what happens when you go further this way or further this way. And so in all likelihood, this is just going to continue to rise. And over here, this is probably going to continue to rise as well. So what we thought looked like maxima actually were not maxima at all. They were, in fact, just higher elevated points. And we only obtain one critical point, xy equals 0, 0. If I wanted the z value, I could plug in 0, 0 into my equation. 0 squared plus 1 over 0 squared plus 1 is equal to 1. So if I wanted the z component in here as well, now I know that that's 1. So to compute the d-test, I need the partial derivatives once again. So now I need the partial derivative. I'll press the back key here. And now I will just type in the derivative with respect to x, second derivative with respect to x. And the beautiful part is that it comes out nice and simplified as well. So 2 over y squared plus 1. So the partial derivative with respect to x twice is 2 over y squared plus 1. And now I'll do the same thing for y. This one's a bit more complex looking, and it's a good thing we didn't have to do this by hand. We get f sub yy is equal to x squared plus 1 times the quantity 8y squared over y squared plus 1 cubed and then we have minus 2 over y squared plus 1 quantity squared. All right. So just double checking that we have that input correctly, y squared plus 1 cubed minus 2 over y squared plus 1 squared, and that's the entire quantity. Now we'll compute the mixed partial derivative, and we'll do that in the same way. We'll just change this down here to dx dy. And we obtain negative 4xy over y squared plus 1 squared. Okay, now we're ready to run the d-test. So we need to compute d of 0, 0, which will be the second derivative with respect to x, evaluated at x equals 0, y equals 0, times the second derivative with respect to y, evaluated at x equals 0, y equals 0, minus the mixed partial derivative evaluated at 0, 0 squared. And here we go. So in plugging in 0 for x. Well, wait a minute, there is no x here. So there's no place to plug in that x, and that's okay. You can actually do this. If this makes it easier to see, you could just add a 0x on there. And now you have a place to plug in an x, but 0 times any value of x will be 0. So the bottom line is that the value of x does not come into play in this second partial derivative. So plugging in 0 for y, I get 2 over 1, which is 2. Times f sub yy at 0, 0, 0. So here I'll get 1, because 0 squared is 1, 0 plus 1 is 1. Here I'll get a 0 in the numerator, so this whole thing will end up being 0. I'll get 0 over 1. And here I will get minus 2 over 0 squared plus 1 is 1 squared, which is 1. So I get negative 2. Okay, and then now I'll have minus the mixed partial derivative evaluated at 0, 0. And you can see here that if I plug in 0 for x and 0 for y in the numerator, I'll get 0 in the numerator, I'll get 1 in the denominator, but that's just going to be 0 squared, which gives me negative 4. And since the d value is less than 0, this again is a saddle point. So, this is less than 0, so since d is greater than 0, means that the point 0, 0, 1 is a saddle point. Now I'll point out one thing here, and then you can kind of see the saddle. Maybe you can see that there's a little bit of a bump there. So that once again is a saddle point. Now, if your d value came out to be bigger than 0, there are two possible situations. So in order for us to have a relative max or a relative min, the d value would have to come out bigger than 0. But then you have to do one more thing. You have to check or compute the second derivative at your critical point. Now, the beauty of this is that we already have that computed. In our case, f sub xx at our critical point is positive 2. So we can actually obtain that right from here. We look at the value of d. If it were to be bigger than 0 and the second partial with respect to x at our critical point is negative, then we have a relative max. However, if our d value is bigger than 0 and our second derivative with respect to x at our critical point is bigger than 0, you would have a relative minimum. Now there's one situation, and that's the bummer situation. If you get d exactly equal to 0, the test simply does not allow you to conclude what type of critical point that is. All right, we'll go ahead and stop here.